Hello friends, welcome again to the tetrahedron chemistry classes. So guys, in today's class I am going to discuss some spectroscopic problems from the previous year CSIR NET examinations. And so far I have planned that I'll cover all the spectroscopic problem questions, spectroscopy questions which have been asked in the previous year CSIR NET examinations before your June 2021 examinations, right? I will try to cover from June 2011 to June 2019. Up to this, I will try to cover those questions. So today actually I am going to discuss, you can see here, today I am going to discuss this problem from the 2011 examination, whether it is the June examination or the December examination. So this is the first problem. You see the absorption at lambda max 279 nanometer and molar absorptivity, that is epsilon having the value of 15 in the UV spectrum of acetone, is due to the pi to pi antibonding transitions, non-bonding to pi antibonding transitions, sigma to sigma antibonding transitions, or pi to sigma antibonding transitions. So what actually, which is the correct answer in that case? So before going into the details of this question, you should know, first of all you should know, this is your acetone molecule CH3, okay, and this is O, this is CH3, okay, and this lone pair is present here, okay. And you know, the generally we only consider those transitions which requires actually very low energy, and you know the low energy correspond to the higher wavelength. So obviously these lone pairs which are present on the oxygen, they are the lone pair on the oxygen, they are the most loosely held. So they actually we can consider this transition, right? That means non-bonding your electron will be excited to certain position. So your what could be your answer in that case? Okay, so this is something very important. So first of all, you see you should know this thing. If you have the acetone, so what are the most fundamental transitions? Say this is your pi bonding molecular orbital, okay, and here this is the non-bonding region, and at the top you are having the pi anti-bonding transition, okay. So in case of the carbonyl compounds, right, in case of the carbonyl compounds, you have two kinds of the important transitions which are of importance. Okay, first transition is this one, which is happening from your pi bonding to pi anti-bonding, okay, and this transition actually occurs somewhere around at 190 nanometer, and this transition is allowed transition. Since it is the allowed transition, so obviously it will have the little higher value of the epsilon max. And the second transition which is important in that case is the transition from non-bonding electrons to the pi anti-bonding. So this transition is basically the forbidden transition. This transition is the forbidden transition, and lambda max for this transition is somewhere around 280 nanometer. So only these two transitions are important, of uttermost importance for the carbonyl compounds. They are most studied one, and in fact this non-bonding to pi anti-bonding transition is the most studied one, and it is actually of quite importance, right? And for this actually you see the lambda max is also somewhere around 15. So this is also given here 15. So what you can do, you can write the lambda max for this one also, okay. This is 15, and this can be easily differentiated with this one, because this pi bonding to pi anti-bonding transition is having this lambda max of epsilon max of 17. So in that case you can see here your correct answer is the option number B, non-bonding to pi anti-bonding. But it's a theoretical question, and if you have learned or if you have studied this particular question, only then you will be able to answer such type of the questions. Otherwise it would be impossible for you. And whatever the explanation which I have given in that case, this is given in the Pavia Lampen book, spectroscopy by organic spectroscopy by Pavia and Lampen. So in that particular book this is given, this question is given as such. Okay, now moving to the next question. This is your second question. Right. Okay guys, so this is your second question, again taken from the June 2011 examination, and what the question says, you see, an organic compound having the molecular formula C7H12O2 exhibited the following NMR data. So NMR data is given here in that case 7.10, and it is corresponding to the one proton only, and it's a doublet, and for this the J value is given 16. So see, you may have the little bit confusion, why is dt, what is the meaning of this dt, and why this is the second your coupling constant is given here. So there is no need to worry about that. You only focus on this 7.10 and this value of the coupling constant, which is your 16. And second data is again given for 5.1, again you are getting the signal at 5.90, and it is corresponding to the one proton, again the J is the 16. So this question is basically solved by using the value of the coupling constant. Okay, so only if you focus on this one, and first of all you see all these compounds are the esters. So this is the ester moiety, this is also the ester moiety, this is also the ester moiety, and this is also the ester moiety, and this ester moiety is in conjugation with the double bond. Here you see, here this is in conjugation with the double bond. Okay, this double bond is here. So basically this is the alkene part, this is also alkene part, this is also alkene part, this is also alkene part along with the ester. So what important information actually you are having in that case? So remember this thing, if you have the simple alkene, right, these two hydrogens are here, this is the simple alkene. Okay, and in case of this particular alkene, if it is like that, so what would be the J value for this one? So please remember this particular point. See, if you focus on this hydrogen, and if you focus on this hydrogen, so these are the trans hydrogens, right? And for trans hydrogens, the 3 bond coupling, why it is the 3 bond coupling? You see, bond number 1, bond number 2, bond number 3. So it's a 3 bond coupling, that's why 3 is here. J value is given here, and the value of this trans coupling is roughly around 11 to 18 hertz. Please remember, it is 11 to 18 hertz. So if you go for the cis coupling, right, cis coupling, so say this, I can label, say this is A, this is B, this is C, and this is D. Now if you are focusing on the cis coupling, that means your coupling constant would be in the cis range actually, right? So A and B. So 3 bond coupling, that is cis, and it will have the value approximately 6 to 15 hertz. Okay, and now see, please remember one thing, whenever you have the J value for the alkene, whenever you are having the J value greater than 15, so it will always correspond to the trans alkene. Please remember. Okay, so in that case you see what the J value is given, J value is 16. Okay, and another J value is here you can see the 16. So 2 signals you are getting for the 2 different kinds of the hydrogens, and these 2 hydrogens must be trans in nature, right, because it is greater than 15, and you know this is for trans. So I can write trans here, I can write trans in that case, and here in that case I can write cis. Okay, so the data actually, the coupling constant suggesting, the coupling constant is suggesting that your alkene is trans in nature. When it is trans in nature, you can see here, you can put some hydrogens over there. So you can put one hydrogen here, it is trans, another hydrogen, it is also trans. Okay, then you can go for this one, this hydrogen and this hydrogen, these 2 are the trans. So now in that case you see, this is hydrogen, this is hydrogen. So this alkene is cis, and again you see this hydrogen and this hydrogen. Okay, so this is also cis, but cis cannot be your answer. So immediately what you can do, you can immediately conclude that okay, B you can ignore and D you can ignore, because they are the cis one and the coupling constant is suggesting the structure is the trans. So what we can do, we can remove the B and D, option B and D from here. Okay, we can remove this one. Now there is a competition between these 2. So again I am removing this one also, I don't need this. Okay, just like that. Now what I can do, now I can move further to solve this particular question, because my answer either A or C, we can recognize this easily. So if you convert this structure like that, say this is CH3, this is CH2. Okay, and after that you are having carbon, double bond, carbon, and one hydrogen is here trans, another hydrogen is here trans, and after that you are having your ester moiety. So you can write O, C double bond O, CH2 CH3. So this is the first structure, and for this particular structure you can again draw, this is CH3 and this is CH2, and now this is your alkene moiety, which is the trans one. So you can put one hydrogen here, another hydrogen here, and then you can connect it with the oxygen and then your carbonyl group, and this is CH3, right, CH2 CH3. So this is these are the two structures. Now if you clearly focus, if you see the proton NMR spectrum, obviously you will get the singlet for this one, okay, and similarly sorry, not singlet, very sorry, not singlet, you will get a triplet for this one. Why triplet? If you apply the n+1 rule, so here you can see here on the next carbon two hydrogens are there, so you can apply the n+1 rule, okay. So if you apply the n+1 rule, it simply gives you 2 + 1 equals to 3, that means it is a triplet. So this is the triplet, and for the same region, this particular, which is the center CH2, it would be a multiplet M. Why multiplet? Because you see this can couple, these two hydrogens can couple with these three hydrogens, similarly with these three hydrogens. Say for example, right, I am assuming that these two couple with this one, it will give you a doublet, and this doublet will again then split it by these three, one, that means quartet of the doublet, and so it will be a multiplet. So this will be a multiplet for you. I hope this is clear to you. There is no need to go for this one and this one, we have already assigned these are the trans hydrogens, okay. There is no need to go in the detail of these things. Similarly, if you see here, this will get a triplet and this will get a quartet, this will get a quartet, okay. Similarly here, this will get a triplet, this will get a multiplet, and this will get a quartet, and this will get a triplet, okay. Now the important thing is that, see, first of all we can see whether it is happening or not happening. So you see here 3 proton triplet, 3 proton triplet. So it's a 3 proton triplet, but 3 proton triplet is also here, so we cannot actually differentiate in between two. Then you can see here 3 proton triplet for the second one. Now you can see here 2 proton multiplet at 2.10. So it's a 2 proton multiplet here and 2 proton multiplet here also, okay. So you see the it is not actually suggesting clearly. Now the important conclusion which we can draw from the chemical shifts is very important. So for example, first of all, you should know one more thing, guys. Alpha hydrogen to the carbonyl group, alpha hydrogens, okay, of ketone, alpha hydrogens of ketone, they will have the chemical shift somewhere around 2.4 ppm. Please remember 2.4 ppm. So what it is suggesting that, see, this is carbonyl moiety, this is the carbonyl group, these are the alpha hydrogen. So they must have the chemical shift around 2.4 ppm, okay. And now you can see here in the second question. So here your quartet, 2 proton quartet at 2.4. Let's check whether it is there or not. So 2 proton quartet at 4.1. Here you can see. Again, if you move here, okay, you are getting this thing actually. 2 proton quartet at 4.1, but you are not getting at 2.4. Let's check for this one. Let's check for this one actually, right, whether I have drawn this structure correctly or not, okay. Let's check this one. Say did I make any mistake? Yes, I made a mistake here actually. So let me correct it first. No issues. This is carbon double bond oxygen and this is oxygen. So basically what I did, C double bond O. Okay, this structure is corresponding to this one, and this structure is corresponding to this one. Very sorry. Now it is clear. You see, this oxygen and this oxygen connected with the CH2, CH3, and for this one, this is your carbonyl, and this is carbonyl, this is CH2, CH3. Sorry guys. So this one actually, this structure is corresponding to this one, and this structure is corresponding to this one, right? Now let's check the chemical shift of these two. Now you can see here these CH2, this CH2 is connected with the electronegative oxygen, so it should be most downfield. It should be most downfield, right? When compared to this CH2, because this carbonyl is not that much of electron withdrawing ability, okay, compared to this oxygen. So this is highly electronegative, and this carbonyl is not that electronegative, so it is upfield at 2.4 ppm, but due to this oxygen it is downfield, it is deshielded, and hence it should be very downfielded one. And when it is in the downfield region, definitely this will have the signal around somewhere at 4.1 ppm, and this is what given here. Actually you see here 4.1 2 proton quadrate, so it's a 2 proton quadrate. So it is looking like that your option A is the correct answer in that case, okay. So you can mark this option A as the correct option. So you see, this is not a very actually simple problem. You have to apply lots of concept in it, spin multiplicity and your deshielding effect and the coupling constant, right? All these things. I hope this is clear to you. Now moving to the next problem, what it says. Okay, this is your next problem. Right, this is I hope this is clear. This is the structure, this is the problem. In a broadband decoupled 13C NMR spectrum, the number of signals appearing for the bicyclooctane A to C respectively are. So it's a bicyclooctane, it is also a bicyclooctane, it is also a bicyclooctane. Different forms are given here. So first of all you can mark them. See 1, 2, 3, 4, 5, 6, 7, 8. 8 carbons are there. Similarly for this one, 1, 2, 3, 4, 5, 6, 7 and 8. For this one also, this is 1, this is 2, this is 3, this is 4, this is 5, this is 6, this is 7, this is 8. Now let's check how many numbers of signals they can give you. So first of all you should go for this one, right? So this molecule is having the plane of symmetry passing from this particular center. So this is the plane of symmetry, okay, and you can assume that this plane of symmetry is passing through the center of the molecule. When it is passing through the center of the molecule, so what it can give you, it can give you the equivalence to the certain carbon. So what are those carbons? So I am removing the numbering, guys, okay, I don't need this numbering anymore, okay. So due to the plane of symmetry, guys, you can see what can happen. Say this and this, these two are equivalent, okay. And now one more thing, you can imagine, you can put another plane through the center perpendicular to the x-axis, right? So this is another sigma plane, say this is sigma 2, this was your sigma 1, okay. So two planes actually which we have passed, one from here to here and another from here to here. So if you bisect the molecule in that manner, so these two would be equivalent. Now if you put the symmetry plane here, then this and this also equivalent. So what you can do, you can mark this it also as A, and this is also A due to the symmetry regions, right? So this symmetry plane is actually there in between 2 and in between 2, and this symmetry plane is there in between 2, in between 2, in between 2. So they are the equivalent protons, okay, AA. Now you can see here, since symmetry plane is there, so this and this is also equivalent, okay. So what you can do, you can write, say this is type B of the carbon, this is type B of the carbon. So this molecule A is giving only 2 signals in the NMR in the NMR spectrum, okay. Let's check whether it is the 2 signals or some other numbers actually. Okay, one signal for this one also. Okay, signal this one, this one. So one signal, say this is a B, this is the type C and type C. So type A carbons, then type B carbons, and in the center, in the fuse position, type C carbons. So it will give you the three signal. Three signals would be there in the proton broadband decoupled, proton decoupled spectrum. So A should give actually three signals, but this you can see in that case A is given 5, so this cannot be your answer. A is giving 3, this can be your answer. C cannot be your answer because A is giving 3 signal. So you can immediately discard option A and option C from here. Okay, option A and option C you can immediately discard. So now you left with the other two options, right? So what I can do, I can remove these. Option C you cannot be your answer, and similarly option A cannot be your answer. Now you left with the B and D. So now let's check what this will give you. So this is again, you see, you can pass the symmetry plane from here to here. If you pass the symmetry plane from here to here, so what it will give you, say again I have to remove the numbering from here to here. Okay, so I am removing this numbering. Okay, so due to this symmetry plane which we have passed from here to here, this carbon and this carbon, they are the equivalent one. So what you can do, you can say this is type A proton, this is also type A proton, and rest of the things actually are quite clear for you, right? Since this plane is passing from here to here. Okay, so this is also A, this is also A. Okay, so these two are also same. And again this, because this plane is going right through the molecule, so this and this, this and this, they are also equivalent, like these two, they are also equivalent. So this is also A, this is also A, this is also A, this is also A. Say if you don't know the stereochemistry of these bicyclo compounds, so I am giving you the link in the description box where I have explained all these things in the pretty much detail, where you can understand all these things. Okay, now what you left with, you left with this carbon and you left with this carbon. Say this is B and this is B, because again they are in the opposite side of the symmetry plane. Okay, so when so what can happen, only type A proton and type B protons are there, so this will give you the two signals. This will give you the two signal. Okay, so 3 is fine, 3 is fine, 2 is fine, and 2 is fine. So again you cannot make difference actually based on the second molecule. Now you have to move for the third molecule. So this molecule, see guys, before going into the details of this particular structure, I am giving you the very short video of the 2-3 minutes actually, where I can explain the stereochemistry of this fused bicyclooctane with the help of the model. First let's see that particular explanation, and then we'll come back onto the pen and paper to solve the question. Okay, so how we can understand this particular problem in which you have given that cyclohexane ring, and over there two carbons are also there, which makes actually bicyclooctane. So how actually we can understand the stereochemistry? So to start with, first of all, you should have idea about this cyclohexane. So this is the chair form of the cyclohexane. If I slightly tilt it, then you will be able to see all the carbons. Say this is a carbon number 1, this is 2, this is 3, this is 4, this one is 5, and this one is 6. Okay, so these 6 carbon are there. And remember one thing, if you check the proton NMR spectrum, or say in this particular case you are going to see carbon NMR spectrum, so what you can do, what you can remember, it is always true, right? If it is cyclohexane, so this particular carbon, if you start numbering from this end, 1, 2, 3, 4, 5, 6. Okay, so 2 and 6, that means this particular carbon, this one, and the carbon which is just in the rear position to it, they are actually symmetry equivalent. So they will give you the one signal in the carbon NMR spectrum. Similarly, if you go for this particular carbon, right, and the carbon just in the rear position to that, right, so these two carbon are also symmetry equivalent, right? You can put the symmetry plane over there. So they will also give you one signal. Similarly, this carbon and this carbon, they are also they will also give the one signal. So this is the case of the cyclohexane. But if you convert this into the cyclooctane octane like this, say if I make this structure, if I convert this structure into this, right? Okay. Now this is your cyclooctane fused. Okay. So this is your fused cyclooctane. Okay. This is the chair form in that case. Again, you see. Okay. Now what you can do here, you see, if you see here, if I tilt this is quite clear to you. This is your chair form of this one, and these two carbons are there, right? If you try to put a symmetry plane over there in between them, so this carbon and this carbon, these two are also equivalent in nature. Okay, so these two will give you the one signal in the carbon spectrum. So in that case, you can see here what can happen. This particular carbon and this particular carbon, they are same, they will give you the one signal. Okay, and of course these two are same, they will give you the one signal. These two are same, this will give you the one signal, and one signal for this one. If you understand this stereochemistry, right, at this chair form of your fused bicyclooctane, then it is very easy to understand how actually these structures are forming the equivalent carbons. Okay, I hope this is clear to you. So if you see, you can see the symmetry plane here, right, through the air. This will cut from here to here, right? This will pass from here to here. Okay, so if this much of thing you understand, then it is very easy to understand that particular problem. Now let's move on to the pen and the paper to understand the things little bit more clearly. Okay, now I hope this is clear to you, how actually it had happened. So now with the idea which you have actually grasped so far with the help of the models, now it is very easy for you, right? So to put the symmetry plane. So here you can put the symmetry plane here, right? In that case, this will pass here. So when you put the symmetry plane here, say this is type A proton, this is also type A proton. Okay, and then in the models I have already explained to you, this would be equivalent and this also would be equivalent, that is B and B. And similarly this one, C and C, these two would also be equivalent due to this symmetry plane, because you see this actually substitution of the two carbons are there on this particular position, but this substitution is not there in this particular position. So this carbon and this carbon, they cannot be equivalent actually. So this and this, they are the different types of the carbon. Let's call it the carbon type D, and this is the carbon type E. So A, B, C, D, E. So how many signals actually this will give you in the carbon spectrum? It will give you the 5 signals. So now let's check, right? This is the 5 signal, but this is 8. This cannot be your answer. So D is not your answer. Your correct answer is the B. So this is how you can solve these kinds of the problems also. Okay, now moving to the next problem, what it says. Okay, this problem again I have taken from the June 2011 examination. In the mass spectrum of the dichloro benzene, the ratio of the peaks at M by Z value 146, 148 and 150 is this. Intensities ratio is the question is asking. Okay, so in that case, you see when you have the chlorinated compound, then you will have the M plus 2 peaks, right? 6 plus 2, 8 plus 2 again, right? So this problem, guys, I have solved in the pretty much of detail. So I am giving you the link in the description, and also the link is flashing at the right hand top side, right top. You can go through that particular link, isotopic peaks in the NMR spectrum. Okay, you can go through this particular lecture, then you will be able to understand these kinds of the problems in the pretty much detail. I have also solved this problem in that particular lecture also, and I am also giving you the link in the description box where you will find the exact explanation for this question also. Okay, now moving to the next question, which is this one. Right, this is the question. You can see what it says. In the 19F NMR spectrum, fluorine NMR spectrum, of phosphorus pentafluoride, the number of signals and the multiplicity at room temperature are. Okay, so whether it is one signal and spin multiplicity is singlet, one signal or doublet, two signals or doublets, or two signals or the singlet. So for this actually you have to draw the structure. Right, this is your phosphorus, and you see this is the fluorine, this is another fluorine, this is another fluorine, just like that. It's a trigonal bipyramidal structure, and this is the fluorine number 5 and this is the fluorine number 5. And be careful, the question is asking that at room temperature how many signals you will have. At room temperature, see, at room temperature nearly about 25 degrees centigrade, there is enough energy present in the molecule, and the interconversion of the hydrogens, interconversion of the fluorine will occur. So what will happen at the room temperature? There would be the very rapid interconversion of the axial fluorine. That means axial fluorine will convert into the equatorial fluorine, and vice versa. See, axial can go to the equatorial, equatorial can come back to the axial. So this is very fast, this is very fast, and NMR time scale is slow. So when the NMR time scale is slow, then the NMR instrument is not able to actually pick that interconversion. So that NMR instrument will treat all the 5 fluorine which are present in the molecule equivalent. So for the instrument actually, for these are, for all 5 hydrogen, all 5 fluorines are equivalent. That mean all fluorines will give you one signal. So of course only one signal you will get in the fluorine NMR spectrum. It is not asking the phosphorus NMR spectrum, it is taking only fluorine NMR spectrum. So only one signal you are having. So when you are having the one signal, so option C cannot be correct answer because it is giving 2 signal. Option D is also giving you a 2 signal, it cannot be your correct answer. So correct answer is either A or B in that case. Now you see here, like fluorine, phosphorus is also NMR active. So all the 5 fluorines which are present here, they would be splitted by the one phosphorus present in it, that is N plus 1, that will give you the 1 plus 1 equals to 2. So in the fluorine NMR spectrum of PF5, you will get one signal and one doublet. Okay, one signal and one doublet. So this is one signal and one doublet. So option B is the correct for this one. So this is how you can understand this problem also. Now moving to the next problem, what it says. Okay, this is your second problem. Okay, so what this problem says, an organic compound having the formula C8H10O exhibited the following proton NMR spectral data: 2.5, 3, this. The compound is 4-ethyl phenol, this and this. Okay, you have to see, first of all you have to draw the structures for all these. So how we can draw the structures? Say this is 4-methyl anisole. So this is anisole, that is OCH3, and 4 position you are having CH3. Okay, this is 1, this is 2, this is 3, this is 4, this is 5, this is 6. Okay, then second structure is 2-ethyl phenol. So this is, you see here, OH is the phenol, and at 2 position you are having ethyl. So this is CH2, CH3, and next structure is this one, 4-methyl benzyl alcohol. Benzyl alcohol, CH2, OH, and at 4 position you are having the methyl, that is CH3, and next structure is the structure A, which is 4-ethyl phenol. So this is phenol and this is CH2, CH3. Okay, so before going into the details of the chemical shift, let's check what is actually happening here in that case. Okay, so you will get 3 proton singlet for this one, and for this you will get 2 proton doublet, because these 2 proton will be splitted by the this H actually. Okay, and you see these 2 are sufficient, I think, and this will give you 3 proton triplet, because it is splitted by the 2 protons in the neighboring carbon, and this will give you 2 proton quadrate. Why 2 proton quadrate? Because 3 hydrogens are there, n plus 1 4, 3 plus 1 4, so this will give you this one. Okay, see, if you are watching this video for the first time and you are a very newcomer in the field of the NMR, in the learning of the NMR spectroscopy, so you may find little difficulty in understanding the splitting pattern. So for this you have to actually learn the basic things first, and you can type in the YouTube NMR spectroscopy by tetrahedron chemistry classes, where I have explained all the basic things also. Okay, you can go there. Okay, so and this is I think quite sufficient, and this is 1 proton singlet. Now coming to this one, this will give you 3 proton triplet, and this will give you 2 proton quadrate, and this will give you 3 proton singlet, and this will also give you 3 proton singlet. Now let's check 3 proton singlet and 3 proton singlet. That means you are having 2 3 proton singlet, and this molecule is having only 1 singlet, this 4, so this cannot be your answer. Okay, similarly you see here this one, this is also giving you only 1 singlet, so this cannot be your answer. A is also not your answer, and this is also giving only 1 3 proton triplet, this cannot be your answer. So only the fourth molecule, only the third molecule actually, right? See, this cannot be your answer, this cannot be your answer. Okay, but only the fourth molecule is giving actually this singlet here and this singlet here. So 2 singlet only given by this 4-methyl anisole. So your correct answer is 4-methyl anisole. There is no need to go to judge the value of the coupling constant, ortho coupling, meta coupling, or para coupling, and what are the chemical shift. First of all, you should actually try to assign the number of signals actually. So from this actually you are getting this knowledge. Only 2 singlets are 2 3 proton singlets are present only in case of the C, and none of the other 3 molecules like A, B and D will have these 2 singlets. So obviously A, B, D cannot be your answer. C is the correct answer. I hope this is clear to you. Okay, this is the simple problem. Okay, now moving to the next problem, what it says. Okay, this is the next problem. Okay, now this is the problem. The NMR spectrum of AX3 exhibits lines at 2.1 and 2.3 ppm for X types of the protons. Okay, this X are also proton, and 4.1, 4.3, 4.5 and 4.7 ppm for A type of the protons. So this is the A is also proton, X is also proton, measured from the TMS with an instrument operating at the 100 megahertz. The chemical shifts of A and X protons and the coupling constants are respectively. Okay, this is the conceptual problem, and this is the very good problem. Okay, so how we can solve this problem? So it is already given in the question. You see here, it is already given in the question for where the spectrum of X3 exhibit lines for X type of the proton. So for X actually you are getting 2 signals. That means for X it is a doublet. Okay, for X it is a doublet. So what I can do actually to make the things little bit easier, I can write just like that, A X3. So type A proton I am calling HA, and X protons I am calling those HB. Okay, and now if you apply the n plus 1 rule, so for this you will get a quadrate, because in the neighbor you see here this is H, this is HA, and in the neighbor you are having the HB. So 3 HBs are there, so 3 plus 1 4, that means it is a quadrate, and for this one only 1 proton is there, that means 1 plus 1 2, so this will give you the doublet. Okay, so you can write D here. So first of all, you need to understand this thing. So for HB, first of all, for HB, you can make a doublet here. So how I can make a doublet? By following the Pascal's triangle. So this is your HB type of the proton. For HB, you are having signal at 2.1 and 2.3. So please remember, you will always start the lower chemical shift, that is upfield, from the right hand side, and this would be a 2.3. This is the this is basic from the spectrum. And then you are having, say, HA type of the proton, you are getting the quadrate. Quadrate means you are having the 4 chemical shift. Okay, you are having the 4 chemical shift. See, 1, 2, 3 and 4. So you will draw the quadrate for this one following the Pascal's triangles. Say this is 1, this is second, and this is the third one. However, it is not very correctly drawn, but you can understand in that manner. Okay, and the chemical shift you are given 4.1, 4.3, 4.5, 4.7. So you can write the chemical shift also. This is 4.1, and then your 4.3, and then your 4.5, and this is your 4.7. Always start the lower value from the right hand side whenever you are trying to assign the things actually. Okay, so how we can go for the value of the, see, first of all you should calculate the G. So I am writing the calculation of J. Calculation of J. I think this particular problem I have also solved in my NMR spectroscopy lecture somewhere, but I am repeating this problem again. Okay, how we can actually judge the value of this say coupling constant. Okay, so for this actually I am writing for HB type of, okay, first of all HB. So how you can calculate, you can actually take the difference. Okay, what difference you will take? You will see this is 2.3. sorry, I have to like that, I have to write like that, 2.3 minus 2.1, this will give you 0.2. So here you can get the value of J 0.2 for this one. You see, this is 2.3, this is 2.1, and what is the coupling constant? Coupling constant is the distance between the splitted peaks in hertz basically. Okay, in hertz. So I have taken the difference of the chemical shift to get this value of the J. Okay, because it is already given that it is operating at the 100 megahertz, so there is no need to calculate there is no need to complicate the thing. You simply take the difference of these two. Now if you want to calculate the J value, another, see, for this you have to also calculate the J value. So what you can do, you can take the difference between 4.3 and 4.1. so this difference is also 2. How? 4.3, 4.1, that is 0.2. Similarly, you can take the difference of 4.5 and 4.3, again it is 0.2. If you take the difference between 4.7 and 4.5, again it is 0.2. So you can use any of the value for J. So this is 0.2 from here and 0.2 from here. So now it is clear that your J value is 0.2, 0.2. Okay, so this is you are getting this one, but you need to calculate this value in the your hertz actually. So how you can calculate for this, how you can go for this one? Formula is quite simple. Delta nu, that means separation between the hertz, that is equals to nu given, okay, multiplied by the value of the coupling constant divided by the 10 raised to the power 6. Okay, so nu is given to you, that means the instrument frequency, that is 100 megahertz. So you can write 100 megahertz, and you need to convert that megahertz into hertz. So you will write 10 raised to the power 6. J value you have calculated as 0.2, so you can write 0.2 here divided by 10 raised to the power 6. Okay, so if you cancel, then this would cancel. 100 to the 200, and decimal before first point, first last digit, you see 20. So your delta nu is basically what? 20. That means J value is 20. Now let's check whether in which question actually the J value 20 is given. See, J value here, it is 2. It is written there in the question itself. Okay. So this cannot be your answer. Again, this is 10. This cannot be your answer. This is 5. Again, cannot be your answer. But only this question is giving the value of this coupling constant as 20. That is which we have calculated here. So this may be your correct answer. And the chemical shift, now it is quite easy. How we can calculate the chemical shift? Chemical shift is very easy to calculate. Okay. How? See, for doublet actually, right? How we can calculate the chemical shift? So for the chemical shift, I need to remove this part here. So for doublet you can check here 2.1 and 2.3. So chemical shift, you can take the average of this one, 2.1 plus 2.3 divided by 2, that will give you 4.4 divided by 2, that is 2.2. So coupling constant, so chemical shift 2.2. So whether where it is given, see, it is 2.1, not exactly, but it is 2.1. Now another coupling constant, another value of the chemical shift you can calculate. You can take, you can add any of the two. See, you can add any, you can take the, you can add these two and taking the average, or you can take the average of these two, you can take the average of these two, all will give you the same thing actually. So again you can calculate, if you calculate the delta value, so what I can write here, 4.3, 4.1 divided by 2, that means it is 8.4 divided by 2, and this will give you your 4.2. So here you see this is 4.3, 2.1 and 20. So coupling constant is making actually more sense in that case. However, you may have the confusion because it is giving the 4.4 and it is giving the 2.2. So you may consider, okay, this would be the correct one. But see, these differences in the chemical shift are not very much, and it happens in the case of the molecules if you go from one instrument to other. So due to the due to some technicality, or say some other regions or some solvent environment, chemical shift may vary slightly. So you have to go for only the whole number value. You don't need to go the value after the decimal point. But clearly you can see here this 20 is making the big difference. So option D is looking the correct answer in that case, while A, B and C are not the correct answer in that case. So this is how you can solve this problem also. Now moving to the next problem, what it says. Okay. Now this is the problem. What it says. An organic compound C15H14O exhibited the following proton and 13C spectrum, right? So data is like that. For proton you are getting 1, 2 and 3 signals, and for carbon you are getting 1, 2, 3, 4, 5, 6. So let's do it on the basis of the proton NMR spectrum. So guys, it is a well known fact, you all knows, whenever these benzene types of the compound are there, so your signal would be at 7.2 ppm. But this proton NMR spectrum, what it is showing, it is showing one signal at 7.2 ppm and second signal at 7.7 ppm. That means two signal in the aromatic range. So two signals, see, I can write here answer, two signals in the aromatic region, two signals in aromatic region. Okay, now let's check the questions actually. Okay, see guys, you can see, if you put the symmetry plane here, from here to here, say I have put it the symmetry plane from here to here, so this part and that part are equivalent, so you will get the one signal for this benzene, and since this benzene is also equivalent to this one due to the symmetry plane, so these two benzene will give you only one NMR, one proton NMR signal, and but in this question itself it is giving the two signals. That means your say di substituted kind of the benzene must be there. Two signals in the aromatic region suggesting that the molecule is actually the di substituted, but this benzene is mono substituted, this is also mono substituted, and due to this symmetry plane they will give you the same signals. So this cannot be your answer. So you can immediately remove this B from here. So this cannot be your answer, guys. Okay, now moving to the next problem. So B, guys, you have discarded. Now then you can another very important thing. You see here, this benzene is the di substituted, this benzene is also di substituted, and similarly this and this di substituted, this and this di substituted. So any three can be your answer. But remember one thing, what actually it is given here. Say this is principal functional group, this is ortho position, this is also ortho position, this is meta, this is also meta, this is para. And for the same region, this is also ortho, this is ortho, this is meta, this is also meta, this is para. Okay, and for this question also you see, this is ortho, this is ortho, this is meta, this is para, this is ortho, this is ortho, this is meta, and this is para. Okay, and this is ortho, this is ortho, this is meta, and this is para. Okay, and similarly if you take this particular substitution, then this is ortho, this is ortho, this is meta, this is para. These are the things are there. Now the important thing which you should know in that case, what is given here, the J value, the coupling constant is 8 Hertz. Coupling constant is 8 Hertz. And what this coupling constant is suggesting. See, I am telling you, if you have the basic idea about this stereo spectroscopy, then you know when you have the ortho coupling between the hydrogens. Okay, then for ortho coupling the J value is 8 Hertz. The J value is 8 Hertz. That means two hydrogens must present in the ortho position. Okay, now let's check here how we can do that. See, two hydrogens must be there. So this is ortho, one hydrogen is here, one hydrogen is here. Okay, but again you see the meta hydrogen is also there and para hydrogen is also there. See, for para also this coupling constant is 8 Hertz, but for meta, if you check for this meta coupling, for meta coupling actually you are having a very low value of say coupling constant. So I can write here meta positions. For meta position you may have the J value around 3 Hertz. So this 3 Hertz is not there in the question. So you can immediately discard the first possibility also. Okay, so what I can, on the basis of the coupling constant, so how what we can do, I can remove this one also, because meta hydrogens corresponding is not actually, see, for this meta hydrogen we are not having the coupling constant. Okay, similarly guys, you can see here for this question also ortho very fine, 8 Hertz, this could be your answer, but two meta hydrogens are also there in that case, two meta hydrogens, but for the meta hydrogens you are not having the coupling constant, so C cannot be your answer. So you can immediately discard C also from here. So you left with only D1, and this D is actually your correct answer. Okay, so you can mark this D as the correct answer. And why I am saying it is correct one, see, this is ortho, so these two hydrogen can couple and the coupling constant is 8 Hertz. This is meta position is not having any kind of the hydrogen, so there is no meta coupling. Okay, however para hydrogen, see, I have made a mistake here, this is the substitution ortho meta, right, this is the ortho, sorry, I made a mistake here. This is meta, this is para. Okay, ortho meta para. Similarly here ortho meta para, and here again see ortho meta para. But you see here at the para position you are having these two. okay, and by substitution is there in that case, okay, and so these two cannot couple, this cannot couple, okay, this cannot couple actually. So see, if you don't apply this much of knowledge, see, if you go for the thing actually which I have explained so far, you can immediately jump into the conclusion that the option D is actually looking the correct answer. Now you can check for the values of your chemical shift also. So this CH3 is there, right? So it is what is written here, 2.4 singlet. So this is actually the singlet at 2.4, okay, and for this also, this is also the same, because they are the symmetry equivalent. So these two methyl will give you the singlet at 2.4, and then your 7.28 hertz, 7.78 hertz. So ortho and para, if you check here, ortho and para, they will have this value of 8 hertz, right? So this is your correct answer, okay. So this is how you can solve this particular problem also, okay. So this is how you can solve. Now moving to the next problem. See guys, if you have a little doubt about this particular problem actually which I have solved, you can comment in the comment section. I'll try to make it more clear, but for now you can understand in that manner only which I have explained so far, okay. Then you see, go for next one, singlet, okay. Okay, one more thing actually which I can give you here, very sorry, how we can differentiate not only the meta and the para position. I can draw the structure actually here, this one, very sorry, don't go for this meta one. This is CH3, this is CH3. So this is CH3, this is CH3. So one singlet for this one and another singlet for this one, but in the question you are having only one singlet, that's why this cannot be correct answer. So you can actually forget about this ortho and the meta coupling and the coupling constant. You can straight away go for the chemical shift. So whatever I explained with the help of the coupling constant, you can ignore that part, you can go for the chemical shift only, okay. This singlet and this singlet, two singlets, but only in the structure, in the question only one singlet is there. So this cannot be your answer. So you can jump into to the conclusion that this is D is the correct answer. See, forget your ortho, meta and para coupling constants, okay. There is no big deal in that. However, you can apply for the initial part also. So this is the next question, what it says. Let's reorient this, okay. I think this is the last question from the 2011, and what it says: appropriate proton NMR chemical shifts for the protons A to D for the following compound as A to D. Okay, I haven't marked the A to D, so let's mark them all. Say this is type A of the hydrogen, this is type B of the hydrogen, and this is type C of the hydrogen, and this is type D of the hydrogen. So A, B, C, D, okay, these three are there. You have to decide the chemical shift. Now guys, first thing you should remember remember that particular thing. Whenever you have given the systems your alpha beta unsaturated carbonyls, okay. However, this is the ester, but it is also having the you see unsaturation at the alpha and the beta position. So try to make the resonance structure for this one. This question is actually based on the chemical shift as well as on the resonance structure. So how we can draw the structure for this. Say you are having CH3 double bond O, this is OCH3, this is H, this is another H. So resonance, it's quite easy, this can come here, this can go there. So what structure you can draw for this? CH3 double bond single bond O negative, OCH3, this is H, this is another H, and this is positive. This is positive and this is negative. and you know this positive sign indicates that the electron deficiency here. When electron deficiency is there, that means there is no shielding of the electron, so it is highly de-shielded. Okay, it is highly de-shielded. And one more thing you can consider here, it is sp2 carbon, right? Now due to this resonance, when it is the sp2 carbon, it is actually the more electronegative, or you can straight away say this is positive charge due to the resonance, and this presence of the positive charge actually is showing the de-shielding. Okay, de-shielding of the nuclei. When the de-shielding of the nuclei is happening, that means this hydrogen should be downfield compared to this one. Okay, so this should be upfield, right, because electrons are there to protect it, and this should be downfield. Okay, and this actually is your A, this is B, this is C, this is D. And one more thing, this D actually is connected with the electronegative oxygen, so this should be the most downfield. D should be the most downfield. Okay, and let's check whether it is the most downfield or not. We cannot say that it is most downfield due to the presence of the oxygen, but it is downfield actually. Okay, now compare HA and HB. Which one is the downfield in the question? So here in that case, HA is 5.7, HB is the 6.8, so it is downfielded. B is downfielded here, so I can write D here for the downfield. Okay, and if you compare A and B here, again it is also the downfield, so this can also be your answer. But again you see this is 5.7, this is upfield, so this cannot be your answer. B at 5.7, this A cannot be your answer. So you can discard the possibility of A and the possibility of B. Now you check which one is correct, C or D. Let's check. Let's move to the another chemical shift actually, right? So how we can do that? This OCH3, right? Type D proton, it is connected with the oxygen, so it should be downfield when compared to the C. This is the methyl, this is also methyl, but this methyl is here you see connected with the carbon, and it will give you the singlet. Okay, but it should be upfield. It should be upfield, and this should be downfield when compared to the proton C. The proton D should be downfield. So D at 3.9, and here D at 2.1 and C at 3.9. So according to the chemical shift actually, this actually C should have the chemical shift of 3.9, and this should have the chemical shift of say no, not C. She should have 2.1. Sorry, it should be upfield, guys. It should be upfield. So it should be 2.1, and this should be actually 3.9, and this A, this B I have already decided it is the downfield. Okay, so your B must be downfield, that is at 6.8. Okay, and this A again, it is downfield, it is upfield when compared to this one, that is 5.7 ppm. Okay, see, you know the alkene resonates from 5 to 7 ppm. Alkene protons resonate from between 5 to 7 ppm. So their chemical shift must be for HA and HB. The chemical shift must be from 5 to 7. So it is 5.7. It is 6.8. Why 6.8? Because due to resonance, here electron deficiency is there. So it is highly de-shielded. De-shielded means downfield. That's why it is having the higher value. It is having the lower value. And you see, this is CS3. This is CS3. This CS3 is connected with the oxygen, which is downfield. Oxygen means electron richness is there, so electron deficiency is there, but this deficiency must be greater than this actually the positive charge which is coming from the resonance. Okay, so this should be actually the downfield, so it is at 3.9, and it is slightly upfield, that is at 2.1. So option D is in that case is the correct answer. Okay, so these are the problems which have been asked in the 2011 examinations, but nonetheless these questions are very important to practice. Okay, I hope you like the lecture, and I'll meet you in the next class with the different spectroscopic problems, or maybe from 2012 examinations. Okay, so that's it for today. Thank you very much.